Hello, this is Dr. Hanaa Assil, and this is Unit 4 of A2 Chemistry at Excel, and we're talking about spectroscopy. Remember that spectroscopy includes mass spectrometry, proton NMR, carbon-13 NMR, and infrared radiation. Another kind of spectrum is nuclear magnetic resonance, or NMR. And the NMR is a kind of spectroscopy that measures absorption of radio waves by the nuclei of atoms. You should realize that carbon-13 NMR is the one that detects carbon-13 isotope of carbon in a molecule, and proton NMR detects the hydrogen nuclei with different environments. So we have two types of NMR. The NMR for carbon-13 and the NMR for protons. Now, the idea is a nucleus with an odd number of nucleons has nuclear spin, and this causes a weak magnetic field. So, which nuclei have odd number of nucleons? A hydrogen nucleus will have only one proton. So this is an odd number of nucleons. So hydrogen nuclei will have a spin. Carbon-12 does not, because it doesn't have an odd number of nucleons, but carbon-13 will have an odd number of nucleons, so the nucleus will have a spin. And that means when the nucleus is aligned with the external magnetic field, it can absorb energy, and the kind of energy it absorbs, remember, are radio waves, and flip. So when the nucleus absorbs the energy and flips, this gives a signal, and that is our NMR spectrum. So to obtain an NMR spectrum, the sample is placed in a magnetic field. As the magnetic field is varied, the nuclei in different environments will absorb different amounts of energy and flip at different field strengths. And this is recorded as an NMR spectrum. So if he says which type of radiation is used in the NMR, of course we said which type of radiation is used in the NMR. These are the different types of radiation, but for the NMR, we use the radio waves. The radio waves used in proton NMR, what do they do? You should remember that what they do is they cause the hydrogen nucleus to change its spin state. So it absorbs energy and goes to the higher energy level and flips, so it changes its spin state. Okay, so let us take a look at carbon-13 NMR first. The carbon-13 NMR will show a single peak for each chemically non-equivalent carbon atom. What does that mean? It means that if we're looking at something like pentanone, what is pentanone? This is pentanone. Now, how many types of carbon atoms do we have? We have one that is CH3 that is further away from the C double bond O. So this will give a peak that is at the beginning on the right of the spectrum. Now, as we go nearer to the electronegative element, which is oxygen, then the peaks shift more to the left. So we have a peak for the CH3, that's one type of carbon, for the C of the CH3. There is another peak for the C of the CH2, and there's another peak for the CH2 that's right next to the C double bond O. There is a fourth peak for the C that is attached to the O, and remember that whenever it's attached to an electronegative element, it is furthest down to the left. So the peak for that carbon is on the left of the spectrum. And then we have another peak for the carbon that is attached to the three hydrogens next to the C double bond O. So the number of peaks indicates the different types of carbons, or we say the carbons that have different environment. So if we look, for example, at hexane, now hexane is a chain with 6 carbons, but this chain is symmetric. Can you see that it's symmetric? So I have a CH3 on the right and a CH3 on the left. Both of them will give me one peak. They are equivalent. there is a CH2 on the right and a CH2 on the left. So both of them will give another peak. These two are equivalent. And then the two CH2s in the middle are equivalent. So actually for hexane, I end up with only 3 peaks because I have only 3 types of carbon atoms or 3 different environments for the carbon atoms. For 3-chloropentane, how many environments do I have? Well, 3-chloropentane, I have a carbon that is attached to the chlorine. That will be the furthest to the left. We said the carbon attached to the electronegative element is furthest to the left. Then I have the CH2s that are next to it. That will be to the right of that. And the CH3s on both ends are equivalent and they will give a peak that is on the right of the spectrum. Now, these peaks are drawn relative to what we call tetramethylsilane. Silicon with 4 methyl groups is called tetramethylsilane. If you look at the molecule, you can realize that all 4 carbons are equivalent. So all of these 4 carbons will give only 1 peak. And also when we talk about the proton NMR, all the hydrogens also in silane are equivalent. So all of these hydrogens will give only 1 peak in the proton NMR. And the peak for the silane, whether we're talking about carbon-13 or proton NMR, the peak for the silane is furthest to the right, and we give it a chemical shift of 0, and the shifts of all the other atoms are relative to tetramethylsilane. So the chemical shift indicates the functional group. So the peak for C single bond C, this is furthest to the right from 0 to 50. Then we said as we have a more electronegative element, then the shifts become furthest to the left. So we have a shift for the C single bond O, a shift for the C double bond C, and a shift for the C double bond O. Again, you will have this in your data booklet. Please learn to use it. It gives you the position of the peaks for each of these functional groups. And again, all of these are relative to tetramethylsilane. So for example, if we're looking at the carbon-13 NMR for ethanol, how many types of carbon do we have in ethanol? We actually have 2 types of carbon. We have the carbon that is attached to OH, and we have the other carbon that is attached to 3 hydrogens. So there will be 2 peaks in my carbon-13 NMR, and the peak that is further to the left, which is around 60, this is the one for the carbon that is attached to the oxygen. So we said the one attached to the electronegative element is further to the left. If we want to use carbon-13 NMR to distinguish between propanone and propanal, okay, so what do we have? In propanone, if you can see, both CH3, both carbons in the CH3 are equivalent. So the both carbons for the CH3 will give you only 1 peak. And then you will have a second peak for the C that is attached to the O, the C double bond O. So in propanone, I will have only 2 peaks because I have only 2 different types of carbons, or 2 chemically different environments. For propanal, how many environments do we have? Well, the CH3, the carbon for the CH3 is different from the carbon for the CH2, and it's different from the carbon that is attached to the double bond O. So in this case, for propanal, I will actually have 3 peaks in the carbon-13 NMR. Another question says I should distinguish between all of these alcohols. So how can I distinguish between the alcohols? I can distinguish between them by the number of peaks. So the different chemical environments for each carbon. So he's saying which of these will give the spectrum that is shown? Well, so I'm looking for something that will give 3 peaks. So let's look at A. how many different carbons do we have in A? We have actually the CH3, that's one, the CH2, another CH2, another CH2 that is attached to the OH. So that molecule will actually give me 4 peaks, not 3. What about the one in B? The one in B will have also 4 peaks because all of these carbons have different environments. What about C? Well, let us take a look. These 2 carbons are the same, so both of them will give me 1 peak, and then I have another for the CH, another for the CH2. So actually, this is the one that will give 3 peaks. While in D, I have how many? In D, I have all the CH3s are 1 peak, and then the CO is another peak. So actually, the one in D will give you only 2 peaks. So the one that will give 3 is the alcohol in C. The compound menthol has the structure shown. Which of the carbon atoms is responsible for a peak at 72 ppm? Remember that we said the one for 72 is the one that has an OH. So if you look at this is the data booklet that you will have. The one for the OH is the one that is around 70 something. So where is the carbon attached to the OH? That is the one that is Q. Okay, this question says compound X gave an orange precipitate with Brady's reagent. Remember, Brady's reagent is the same as 2,4-dinitrophenylhydrazine. And we said that the one that gives an orange precipitate with 2,4-dinitrophenylhydrazine, but not with toluenes, then we're talking about a ketone, not an aldehyde. When X was added to a solution of sodium hydrogen carbonate, effervescence occurred and the gas evolved, turned lime water cloudy. So which compound will react with carbonates or hydrogen carbonates and give out carbon dioxide gas? That means I have a carboxylic acid. Now he's saying that the empirical formula of X is C4H6O3. The carbon-13 NMR gave only 4 peaks. And he's saying deduce 2 possible structures showing how this information supports your answer. So we're looking for something that has 4 carbons. And it should have a ketone and a carboxylic acid. And it should have only 4 different types of carbon or 4 different environments for the carbon. So these 2 structures would fulfill all of these requirements. Then another question says carbon-13 NMR spectroscopy provides information about the structures of propanal and the propanone. Identify the chemical shift and carbon environment of 1 peak you would expect to see in both. Of course, both propanal and propanone will have a C double bond O, and this C double bond O is at this kind of chemical shift. So you please refer to the data booklet to record the chemical shift range. Now, state the number of peaks you would expect to see in the carbon-13 NMR. For propanal, how many different kinds of carbon do we have? We have the carbon that's attached to 3 hydrogens, and the other carbon that's attached to 2 hydrogens, and the carbon that is for the C double bond OH. So I have 3 types of carbons for propanal. While in propanone, I will have 1 peak for the C double bond O, but I will have only 1 other peak for the 2 other carbons because they're equivalent. The 2 CH3s on both sides of the C double bond O are equivalent. So I will have only 1 peak for these 2 carbons plus the peak for the C double bond O. Another question says compound B, an isomer with molecular formula C6H12O2, contains a ring of 6 carbon atoms. The carbon-13 NMR has only 2 peaks. So we have only 2 types of carbon, one of which is at 69 ppm. And we said a peak at around 60 something in the carbon-13 NMR probably means that this is an alcohol. So draw the structure of compound B. So you're looking for something that has an alcohol, because this is where you're going to have a peak for carbon-13 NMR for the carbon attached to an OH. And if you have a ring with two oxygens, that means I will have something like this, which is symmetric, because that means I will have only how many peaks? Two peaks. I have one peak for the carbon that has the OH and another peak for the other CH2s on both sides, which are all equivalent. Then the other kind of NMR is the proton NMR. So again, he will give you in the data booklet this list, and we're going to use this to determine the structure. But we have two types of proton NMR. We have something called a low resolution proton NMR, and there is a high resolution. So the low resolution NMR shows a single peak for each non-equivalent hydrogen atom. Remember, we're now talking about proton NMR, so we're looking at the hydrogen. Okay, so if I have, for example, a low resolution proton NMR for ethanol, how many hydrogens do I have in ethanol? How many different types of hydrogens do I have in ethanol? I have the hydrogen of the CH3s, I have the other hydrogens of the CH2, and I have the hydrogen that is attached to the OH. In the low resolution NMR, I will have a single peak for each of them. And the one that is nearer to the electronegative element is further to the left. So the OH is usually the one on the left of the spectrum, and any CH3s are usually further to the right, and then I have a CH2 that is next to the OH. I have three different types of hydrogens, or three different environments for the hydrogen. I get one peak for each. The area of the peak, or the height of the peak, indicates how many hydrogens contribute to this peak. So the CH3 peak is higher because I'm talking about 3 hydrogens. The other peak is a little bit lower because I'm talking about 2 hydrogens, and the OH is the lowest because I'm talking about only 1 hydrogen. So this is the low resolution. But if we look at the for example, low resolution of ethanoic acid, how many different hydrogens do I have for the ethanoic acid? I have the hydrogen of the CH3 and I have the hydrogen of the OH. So I will have only 2 peaks in the proton NMR. And of course, because the CH3 contributes, 3 hydrogens contribute to that peak, that is the higher peak. Let's look at some questions. This question is about low resolution proton NMR. NMR involves the interaction of hydrogen nuclei in the presence of a powerful magnetic field with, again, which kind of waves? Remember, we are talking about radio waves. Which of the following has 2 peaks in its resolution NMR? Remember, 2 peaks means 2 different types of hydrogen. So what does dichloromethane look like? This is dichloromethane. Actually, both hydrogens are equivalent. So both of them will give me only 1 peak, not 2 peaks. Ethane, all the hydrogens are equivalent. So this will also give only 1 peak. Methanol, both hydrogens are equivalent. You will have only 1 peak. But if you look at methanol, you will find that you will have a peak for the hydrogens of the CH3 and another peak for the hydrogens of the OH. So this is the one that will give me 2 peaks in the low resolution proton NMR. Now, this question says NMR spectra depend on the number of different hydrogen environments. How many different hydrogen environments are there in this molecule, 2,3-dimethylpentane? Well, let us take a look. You have 2 methyl groups that are equivalent. So both of them will give 1 peak. Can you see that? And then the carbon that is attached to them will give a different peak, the hydrogen that's attached to it. And the other hydrogens on carbon number 3, carbon number 4, carbon number 5, carbon number 6 all of these are different hydrogens. So actually, you're going to have 6 different peaks for 6 different hydrogen environments. How many peaks are there in the low resolution proton NMR of 2-methyl propane to all? This is 2-methyl propane to all. Of course, you can see that all the methyl groups, the hydrogens are equivalent. So I will have one peak for all the CH3s and then another peak for the OH. So actually, I will just have a total of 2 peaks for this molecule. Which compound has 3 peaks with relative peak areas of 3 to 1? Remember that we said the area of the peak indicates how many hydrogens account for it in its low resolution NMR. Well, let's take a look. Propanal will give how many peaks? It will give 1 for the CH3, 1 for the CH2, 1 for the C double bond OH, and these are 3 to 2 to 1. So this is actually my answer. What about the others? This will actually give 2 different peaks because the CH3 on both ends will give 1 peak while the CH2 in the middle will give another peak. What about propane 1-all? Propane 1-all will give a peak for the CH3, a peak for the CH2, a peak for the other CH2, and then a peak for the OH. So this is actually 4 peaks, not 3. For this one, we're going how many peaks? We're going to have actually both CH3s on both ends are equivalent, so I will have 1 peak for the both CH3s, and I will have a peak for the CH that is attached to the OH, and a third peak for the OH. So this will actually give me 3 peaks, but they're not 3 to 2 to 1. They're going to be actually 6 to 1 to 1. So this ratio is wrong. So this is not the answer. Okay. This question concerns 4 organic compounds, the compound which have fewest peaks in the proton NMR. So let us look at the different hydrogens in each of these. For P, we have how many different types of hydrogens? We actually have a total of 5 types of hydrogens. He wants the fewest. Q will have 4 types of hydrogens or 4 hydrogen environments. R is the one that will have 3. S will have a total of 4. So R is the one that has the fewest number of peaks in the proton NMR. Then we have high resolution proton NMR. The difference here is that each peak is split, and the splitting depends on how many hydrogens in the next environment. So if we're talking about ethanol, the CH3, the peak for the CH3, I have 3 hydrogens on the CH3. So we had a peak in that area. But then what is the next carbon attached to? The next carbon next to the CH3 is attached to a CH2. So the carbon next to it has 2 hydrogens. It will be split into 3. So the peak for the CH3 is a triplet. It's a triplet. Why? Because the next carbon has 2 hydrogens. Now, let us look at the peaks in the middle. The peaks in the middle are due to CH2. So these peaks are due to 2 hydrogens, so their area is lower than the peak that is due to 3 hydrogens. But then what is its environment? The CH2 has a carbon next to it on the left that is attached to 3 hydrogens. So this peak for the CH2 is a quartet. The peak for the CH2 is split into 4 peaks because the neighboring carbon has 3 hydrogens. So this we call the N+1 rule. So if my next carbon next door has 3 hydrogens, then I will be split into 4 peaks. The one for the CH3, the carbon next door has 2 hydrogens, so it is split into 3. It's a triplet. Do we understand this? Now, the OH peak does not split. So it's usually a singlet. It's always a singlet. Okay, so if we have a proton NMR spectrum, what we do is we use the chemical shift values to identify the environment of the protons. We said the 0 is given to the tetramethylsilane as a reference. Then the CH3, CH2 will be more to the right, while the ones attached to electronegative elements are more to the left. And then we use the relative area under each peak to determine how many hydrogen atoms contribute to that peak. And we use the splitting pattern to determine how many hydrogens on my neighboring carbon atom or my adjacent carbon atom. So, for example, this question says which compound does not have a singlet in its high resolution proton NMR? So let us take a look at each one. Butanoic acid, will it give me a singlet? Yes, that hydrogen has no, it's attached to an oxygen, so there is no hydrogen on the neighboring atoms, so this will give me a singlet. Butanone, what is butanone? Well, this CH3 has no hydrogen on the neighboring carbon, so that CH3 will give me a singlet. What about butanal? Well, butanal will not give a singlet because the hydrogen of the C bond O has hydrogens on the next carbon. So each hydrogen on a carbon has neighboring hydrogens on the neighboring carbons, so there is no singlet in this molecule. What about butane 1-all? Butane 1-all again will give a singlet for that OH. So the only one that does not give a singlet is the butanal. Compound Z has the structure shown, and he's saying the high resolution proton NMR shows 4 peaks. What are the splitting patterns for this? So this is the molecule. How will the proton NMR be split? Well, you can see that splitting depends on my neighboring carbon. So the CH3 on the right is next to a carbon that doesn't have any hydrogen, so that will give a singlet. Now, the CH2 after that has 2 hydrogens on the neighboring carbon, so it will be a triplet. The CH2 in the middle has 2 hydrogens on one side, 3 hydrogens on the other, so it will split into 6. While that final CH3 has 2 hydrogens on the neighboring carbon, so it is a triplet, so this is my answer. This is another type of questions where he says compare between the spectra of butane 1-all and butanoic acid. So he's saying state 2 differences in the proton NMR, butanol and butanoic acid. So what is the difference between them? You should realize that butanoic acid will have how many peaks? One for the CH3, CH2, CH2, OH, so I have 4 peaks, while butanol has 5 peaks. And then the OH will have different chemical shifts for alcohol and for acid. Another question says use chemical shift data to sketch the high resolution proton NMR of propanoic acid. So he's telling you to draw the proton NMR of propanoic acid. So let's take a look at this. Propanoic acid, first of all, will have 3 different types of hydrogens. One for the OH, and we said the one for the OH is usually to the left at around 11, 12. You can go back to the data booklet to determine the chemical shift for the OH of an acid. And then the CH2 and the CH3s will be more to the right. The CH3 is usually to the right more than the CH2, which is nearer to the electronegative elements. Remember the splitting. We said OH peaks do not split. Now, the CH3 has 2 hydrogens next to it, so it will be a triplet. It will be split into 3. The CH2 has 3 hydrogens on the neighboring carbon, so it will be split into 4, or it will be a quartet. This high resolution proton NMR of ester Z is shown. So this is the structure of ester Z, and he's saying we have different peaks. Now explain the splitting and label which protons are responsible for each peak. Okay, so let us take a look at this. What do we have? We have peaks for CH3, CH3, CH, CH2, CH3. If you look at the different chemical shifts, the one for the CH3 on the left is the singlet at B, because there is nothing on the next carbon next to it. So this is the one that's a singlet. Now, which one is A? A is the carbon that is next to the oxygen. We said carbon that is attached to an electronegative element, its hydrogen will be further down to the left. So that is the A. And it is split how much? It is next to a carbon that has 3 on one side and 2 on the other. So it will be split into 6. 2, 4, 6. So A is what we call a sextuplet, or it is split into 6. Then where is C? C is the one that is CH2 in the middle, and it has 3 hydrogens on one end and another hydrogen on the other, so that is 4. So it is split into 5 small peaks. Now, which one is D? D is the CH3 that is attached to a carbon in which the neighboring carbon has 1 hydrogen, which we labeled A. So D is a doublet. It's split into 2 because the neighboring carbon has only 1 hydrogen. Now, where is the CH3 that is at the end? That is a CH3 next to a carbon with 2 hydrogens, so it is a triplet. Do we understand all of this? I hope it's not too long for you, and thank you for listening, and I hope this was useful to you. Thank you.